Now let's go to quantum numbers. Quantum numbers are values used in describing the position and energy of an electron in an atom. They're very simple here. There are 4 quantum numbers, namely principal quantum number denoted as n, azimutal or subsidiary quantum number denoted as L here. This one principal quantum number. Next is magnetic quantum number. This azimutal quantum number is also called angular momentum quantum number. This one, the second one here. Then number 3, magnetic quantum number. We have that too, denoted as M. And the last one, spin quantum number, S. So let's take a few atoms. And maybe write the quantum number describing maybe 1 or 2 or some of their electrons. Let's go. Number 1, let's take sodium, for example. Sodium has an atomic number 11. Sodium is the 11th element on the periodic table. Now, when you write the shell configuration of sodium, you actually always write 281. But when you write, 281 means first shell 2 electrons, second shell 8 electrons, third shell 1 electron, meaning that first shell 2 electrons, let's denote the electron. Second shell 8 electrons, let's just indicate 8 electrons. Then last shell 1 electron. This means that the K shell, first shell is the K shell, second shell is the L shell, and the third shell is the M shell. We can also call it shell 1, shell 2, shell 3. Any one of this is okay. Maybe letters or numbers. So here, this is shell configuration, but in more detail, the 4 quantum numbers are actually shown and are actually used when we write, our electron configuration in quantum configuration. So let's go. Sodium is 1s2, 2s2, 2p6, and 3s1. This means this is the quantum configuration of sodium. This is the quantum electron configuration of sodium atom. This means that if we were to draw diagrams showing energy levels, the first energy level will be the 1s energy level. Second one will be the what? Second one will be the 2s energy level. Okay, 2s. Next one will be the what? 2p energy level. That one has 3 orbitals. And lastly is the 3s energy level. Now, in each of these energy levels, the electrons are arranged like this. 1, 2, 1s has 2 electrons, 1s2, as I have written here. 2s also contains 2 electrons, 2s2, as we've written here. Then 2p has 6, 1, 2, 3, 4, 5, 6. Notice how I fill my electrons singly first before going ahead to pair them. That's the HUND'S rule. Lastly, the last energy level has 3 electrons. See, in actual fact, what this means is very simple. Let me now quickly show you the meaning of each quantum number. Now, n, which is the first quantum number, indicates n, which is the first quantum number, tells us the shell. We can say shell or main shell, tells us the shell or main shell, or call it main energy level of an electron. N denotes or tells us the shell or main energy level of what? An electron. So when you see an electron's principal quantum number, it tells you what shell the electron belongs to. So the values of n has values 1, 2, 3, 4, 5, and so on, depending on the shell it belongs to. Depending on the shell it belongs to. Secondly, this second quantum number, which is what? L. L is called the principal quantum number. Sorry, I said principal quantum number. L is called the subsidiary quantum number. Let me quickly indicate that here. N is the principal quantum number. N is the what? Principal quantum number. L is now the subsidiary or azimutal quantum number. N is the subsidiary or azimutal what? Quantum number. I wrote that upstairs, so you check. Now, the values of L are dependent on the values of N. So, when N is 1, the values of L are what? When N is 1, the values of L are 0. When N is 1, the value of L is 0. When N is 2, the values of L will be what? 0 and 1. When N is 3, the values of L will be 0, 1, or 2. So that means when N is N, that means when N is, whatever the value of N is, the corresponding values of L will be 0, 1, 2, 3, till you get to N minus 1. So take note of that. So another thing we need to mention here is the essence of all this. What's the essence of L? L tells us what subshell. L tells us the subshell of an electron. What subshell an electron belongs to. L tells us what subshell an electron belongs to. So we are going to go into more details now. So let me now take it one after the other. Let's take it one after the other. Let's say I just pick an electron. Let's say I pick an electron. Or let me explain. Okay, hold on. Let me explain the value of what? Let me explain the meaning of M, which is the what? Which is the magnetic quantum number. The values of magnetic quantum number depends on the value of what? The values of the magnetic quantum number depend on the value of L. So if L is 1, when L is 1, when L is equal to 1, the values of M will be, when L is equal to 1, and L can be 0. When L is equal to 0, let's start with that, 0. When L is equal to 0, the values of M will be 0 also. But when L is equal to 1, the values of M will be what? Let me use brackets here. When L is 1, the values of M will be minus 1, 0, or 1. Also, when L is 2, when L is 2, the values of M, okay, I didn't write M here. I'm supposed to write M here. M is equal to minus 1. So when L is 2, the values of M will be either minus 2, minus 1, 0, 1, or 2. So and so on and so forth. The values of M depend on the values of L. Let's now go to the last one, which is the spin quantum number. For the spin quantum number, there are just two values for the spin quantum number of an electron. It's always plus half. The spin quantum number is always what? Plus half or minus half, depending on, this one tells us, so let me now tell you what the value of M tells you? The value of M tells you the orbitals. S tells us the orientation. So let me go ahead and jot that down. What's it called? Information provided. We'll go back to our example now. Let me just give you this short note. Information provided by each quantum number. Now, each quantum number gives us some information about an electron. So let me do this. Quantum number, then the information it gives us about an electron. So let's do this together. Quantum number and the information it gives us about an electron. Okay, number one, principal quantum number. Principal quantum number. That's N. It tells us the shell an electron belongs to. The principal quantum number tells us what shell an electron belongs to. Okay, let's continue. Number 2, Roman number 2, azimutal or subsidiary quantum number. The azimutal or subsidiary quantum number. The azimutal or subsidiary quantum number tells us the subshell an electron belongs to. So when we start using this, you will appreciate it a lot. It's very, very interesting. So that's number 2. Roman number 3, let's go to the magnetic quantum number. What does the magnetic quantum number of an electron tell us about the electron? The magnetic quantum number. That's what? Azimutal is Z. No, L. Magnetic is M. It tells us the orbital an electron belongs to in a subshell. You know, this one tells us the subshell an electron belongs to in a shell. The magnetic quantum number, this M, tells us the orbital an electron belongs to in a subshell. But the principal quantum number N itself, this one, tells us the shell an electron belongs to in an atom. I hope you are getting the logic. Let me go take that again. When you see the 4 values for the quantum number of an electron, the first one written is what? N, which is the principal quantum number. The principal quantum number tells you the shell an electron belongs to in an atom. When you see it subsidiary or azimutal quantum number, that value tells you the subshell an electron belongs to in an atom. After knowing the subshells usually have orbitals. So the value, the quantum number that will tell you what orbital an electron belongs to in the subshell is the magnetic quantum number. So that one tells you the orbital an electron belongs to in a subshell. Then, when you know the orbital, you now also need to know whether the electron spins clockwise, whether it spins clockwise or anti-clockwise. What tells you that is the spin quantum number. So this one tells you, we call it the spin. This one gives you the spin or orientation. This one gives you the spin or orientation of an electron in an atom. This one tells you the value of the spin quantum number of an electron tells you the spin or orientation of an electron in its atom. So I think we have the basic things we need now. We can go forward with examples. So let me just separate this. Let me separate these electrons or these quantum numbers. Okay, I still have one more line to draw here. Use your ruler for yours, I don't really have. Sorry, this is taking our time. Let me be fast with it so that we can go to the examples. Now, so this is all that we need for the basics on quantum numbers. Let's now go ahead and write. I said we are going to write the value of the quantum number. We are going to write the quantum number values for the electrons of sodium. So which one should we start with here? Let me choose. I like starting from the right. So let me write the value of the 4 quantum numbers. Let me write down the quantum numbers for this electron. This last electron. Now, this electron, as you can see here, is in the 3rd shell. It's in the 3rd shell. This is the 3rd shell here, shell M. This is the 3rd shell. So this is the electron that we are referring to. It's in the 3rd shell. That means it's what? That means it's what? Its N value will be what? 3, because it is in the 3rd shell. Are you getting what I'm saying? That electron is in the 3rd shell. Let me write sodium again so we can have it close by. Okay, Na11, 1s2, 2s2, 2p 6, and 3s1. This electron is in the 3rd shell. This last electron here is in the 3rd shell. So its principal quantum number value will be what? 3. So N is equal to 3 for this electron. N is equal to 3. Now, that's the shell it belongs to. So it belongs to the 3rd shell. Do you understand? 3 means that the electron is present in the what? 3rd shell. Now, let's go to the second quantum number. What's the second quantum number? After principal, subsidiary, L. This one should tell us the subshell the electron belongs to. Now, the 3rd shell has 3 subshells. It has 3s, 3p, and 3d. So that means each of these, we said when n is 3, I said before that when n is 3, the possible values of L are what? 0, 1, and 2. When n is 3, when n is equal to 3, the possible values of L will be 0, 1, or what? 2. So if an electron is in the 3rd shell, that means it will either be inside the 3s subshell, which has, an L value of 0, or 3p subshell, which has an L value of 1, or 3d subshell, which has what? A subsidiary quantum number of 2. But this electron we are talking about in this sodium is in the s subshell of the 3rd shell. So that means its own value, its own value for the quantum number L will be equal to what? 0. I hope you are getting what I'm saying. So since it is in the s subshell, its value for the quantum number L will be 0. So that tells us where it belongs, in the 3rd subshell. So that means it is in the what? S subshell. You understand? So it is in the 3rd shell. The electron is in the 3rd shell, but in that 3rd shell, you have 3 subshells. You understand? You have 3s, you have 3p, and you have 3d, much larger than 3p. But this electron we are talking about is in the S subshell. So its value for the subsidiary quantum number will be what? 0. Because we said when n is equal to 3, the possible values of the subsidiary quantum number when n is 3 are 0, 1, and what? 2. Take note of that. The values of L are gotten from the values of n. The values of M2, which is the next quantum number, are gotten from the values of L. Let's go ahead and do that now. So let's do that now. Now, what is its M value? What's its value for the magnetic quantum number? Now, we said before that magnetic quantum numbers depend on subsidiary quantum numbers. Let me explain that again. I said it before upstairs that magnetic quantum number depends on what? M depends on L. The value of M for any electron depends on its value for L. So we said when L is equal to 0, let me quickly explain that again or recap. When L is equal to 0, M is what? M is equal to 0. But when L is equal to 1, M can be minus 1, it can be 0 or 1. When L is equal to 2, M can be what? Minus 2, minus 1, 0, 1, or what? 2. So here in this case, our value of L is 0, as you can see here. That means the value of M will also be what? 0. So our value, the quantum number, the subsidiary quantum number is 0, so the magnetic quantum number too will be 0. Take note of that. Don't worry, it takes time, but we'll get there. When M is 0, when L is 0, M is also 0. You understand what I'm saying? So that means, although it is in the S subshell, it is also in the only orbital present in the S subshell. You understand? It's in the only orbital. The electron is located in the only orbital of the what? S subshell. The S subshell has just one orbital, so that electron will be placed there. You understand? There's no other room for the electrons, for that electron to sleep in. There's no other room for this electron to sleep in other than sleeping in the S room. You understand? If it was in the second shell now, if it was in this second shell now, or the second subshell of the second shell, it could sleep in the first room, second room, or third room. So its value can be minus 1, 0, or 1. Minus 1 for this room. Look at this thing very well. It's very simple. Minus 1 for this room, minus 1 for this room, 1 for this room. Sorry, 0 for this room, 1 for this third room. Or let me write it on the other side. Minus 1 for this room, 0 for this room, 1 for this room. But when an electron is present in the S subshell, there's no other room it can sleep in other than the one in the middle, which is the 0 room. And its value for M, magnetic quantum number, will be 0. Let's now go ahead and write its value for what? Let's now go ahead and write its value for the last quantum number. The last quantum number is, the fourth quantum number is S, which is the spin quantum number. This electron, if you look at it, the S room can take 2 electrons. This S room can take 2 electrons. I'm coming back here all the time, sorry. This S room can take 2 electrons. One can sleep and face the door. The other one can sleep and face the window. Can you see that? The one that faces the door or is oriented clockwise, we have an S value of +½ This one that faces the window, we have an S value of -½ So even though they have the same value for N, they have the same value for L, they have the same value for M, when it gets to S, they will not have the same value. Because although they are sleeping in the same house, They are sleeping in the same room, they are sleeping on the same bed, but they are not facing the same side. So one will be facing the door, one will be facing the window. So their S values will be different. Are you getting it? We call this orientation. That although they are, you understand, in the same orbital, their orientations are different. This one is said to be oriented clockwise, while this one is said to be oriented what? Anti-clockwise. So this one is oriented anti-clockwise. So that's the meaning of their spins being different. So let's go ahead and write. Because there was just one electron there. Let's go ahead and write its spin value, or its spin quantum number. Its spin quantum number is what? Plus half. So this tells you that the electron, although the electron in its orbital spins clockwise, or you say it is oriented clockwise. So those are the four values for the what? Those are the four quantum numbers of what? Of sodium's valence electron, which is the last electron. You understand? Its principal quantum number is 3. Its subsidiary or azimutal quantum number is 0. Its magnetic quantum number is what? 0. And its spin quantum number is what? Plus half. Can I say that again? Its principal quantum number is 3. Its subsidiary quantum number or azimutal quantum number is 0. Its magnetic quantum number is what? 0 or so. And its spin quantum number is plus half. This brings us back to one of the rules that we learned on what's it called? One of the rules we learned, one of the rules for arranging electrons into atoms that we learned. That rule was the third rule. We didn't discuss it. I said we were going to discuss it later. It was Pauli. That rule was called Pauli exclusion principle. Pauli what? Exclusion principle. And the rule says that no two electrons in an atom, no two electrons in an atom have the same values. No two electrons in an atom have the same values for all four quantum numbers. No two electrons in an atom have the same values for all four quantum numbers. No two electrons in an atom have the same values for all four quantum numbers. So this is the what's it called? This is where this third rule is illustrated. You understand? This is the place where the third rule is illustrated. Third rule used for arranging electrons in an atom of an element. So let's go ahead. We can pick any electron. Let me draw this sodium atom again. Let's take this as example 2. Let me draw the sodium atom again. Let's continue using sodium. Let me draw the sodium atom again. 1s. Excuse me. Can't stop that from moving upwards. 1s2. I'm going to make that bigger. 1s2. 2s2. I don't need to write these two. The electrons inside will tell us what the number is. 1s2, 2s2, 2p, then what? 3s. So let's fill the electrons. In 1, 2, 2s2, 1s2, 2s2, 2p6, and what? 3s1. That's how the 11 electrons in sodium are arranged in its shells and orbitals. So let me take another electron and write its 4 quantum numbers. Choose yourself. Okay, let's pick this one. Let's write the 4 quantum numbers for this electron I've just selected. So first thing you need to ask yourself is that in what shell is the electron located? It is located in the second shell. This is like first shell, second shell, then what? Third shell. First shell has 1 subshell. Second shell has 2 subshells, 2s, 2p. Sorry, 2s, 2p. Then the third shell has 3 subshells, 3s, 3p, 3d. But because we don't have any electron to fill into the p and the d subshells, we don't need to bother drawing them and leaving them empty. So we just stop at the 3s subshell. So this electron we have chosen is located in the second shell, just like this. First shell, 2 electrons. Second shell, 8 electrons. Third shell, 1 electron. So this electron we have chosen is located in the second shell. So its principal quantum number, the principal quantum number of the electron is what? Let me draw the electron here. Its principal quantum number is 2. Let's go ahead and write its subsidiary quantum number. Its subsidiary quantum number, you have to check. If the principal quantum number is 2, when n is 2, the possible values of L are 0 and 1. So 0 will be for the S subshell. 0 will be for the what? 0 will be for the S subshell. While 1 will be for the P subshell. But the electron we have marked, the electron whose quantum number we are writing, is in the S subshell. So its subsidiary quantum number will be what? 0. So this one for the S, this one for the P. Or let's say this one for the 2S, this one for the 2P. So since our electron is located in the S subshell of the second shell, its subsidiary quantum number is 0. Now, next one is the magnetic quantum number. We said before the magnetic quantum number is decided from the values of the subsidiary quantum number. And when L is 0, M is also 0. Although when L is 1, M can be minus 1, 0, or 1. When L is 2, M can be minus 2, minus 1, 0, 1, or 2. But in this case, this is what we have now. Our L is 0, so our M will also be 0. That tells us that the magnetic quantum number of that electron is what? 0. So we write that. Spin quantum number now. Is it pointing upwards plus half, or what? Downwards minus half? This is what we have. It's pointing downwards. So its spin quantum number will be minus half. I think it's becoming fun now and sweet. Let's take another electron. Let's take this electron. Let's take this electron next. Let's take this electron and write it. Let's write the 4 quantum numbers of this electron. Look at my blue color here. Let's write the 4 quantum numbers of that electron. Now, the electron is standing upright. So even before I get there, you know it should be plus half. But let's start from the principal quantum number. What is its principal quantum number? It is located in the what? It is located in the second shell. So its principal quantum number will be 2. It's in the second shell. What's its subsidiary quantum number? You have to check. The second shell, when n is 2, you have to check when the values of L are gotten from the values of n. And when n is 2, L can be either 0 or 1. These are the possible values of L when n is 2. Meaning that an electron located in the second shell can either be in the 2s subshell or the what? 2p subshell. This electron we have marked is located in the 2p subshell. So its subsidiary quantum number will be what? 1. So let's go ahead and write that. Subsidiary quantum number L is what? 1. So now when L is 1, the next quantum number is M. The possible values of M when the value of L is 1 are -1, 0, and 1. So it means when an electron is located in the 2p, in the p subshell, any p subshell has 3 orbitals. So these are the possible values. It can be -1 for 2px, 0 for 2py, and 1 for 2pz. The electron we are discussing here is in the middle, here. So that means its M value will be 0. I hope you are getting that. It's in the 2py orbital of the second subshell of the second shell. So that means its M value, its magnetic quantum number will be 0. Then it is spinning clockwise, so its spin quantum number is equal to half. So just like that, you can choose any electron. Once you write out the quantum electron configuration of an atom correctly, you can choose any of its electrons and write out the 4 quantum numbers for that electron. You understand? Try to have fun. Let me just give you one example here. It's very easy. Let me give you one example here. Let's say I'm talking about hydrogen, helium, lithium. Let's say I'm talking about lithium, beryllium, boron, carbon. Okay, let's talk about carbon. Carbon is 6. The quantum electron configuration is 1s2, 2s2, 2p2. That's 6. If I was drawing, my diagram would look like this: 1s, 2s. Sorry about that. 1s, 2s, then what? Okay, I think I made that too high. 1s, 2s, then what? 1s, 2s, then 2p. 1, 2, 3. So 2s, 2p. Now, if I'm, when filling, this is 1s2. So 2 electrons. Also 2s2. 2s2 is what? Also 2 electrons here. Then 2p2 will be 1, 2. According to HUND'S rule, when filling electrons into orbitals in the same subshell, this is a subshell, but these are all orbitals. This is 2px orbital, this is 2py, this is 2pz. So when filling electrons into these orbitals of a subshell, you fill the electrons in singly before pairing takes place. So I'm not going to write 1, 2 for these 2p2 electrons. I'll fill them singly first. You understand? Then when they are all fully filled singly, I cannot start pairing. But I've already filled all the electrons I have. So the third orbital will be empty. Now, choose any electron you like here too. Let me choose this. Let me choose this electron in red. You understand? This electron I've chosen. Okay. Let me draw it here. It's facing down. Let me now write its 4 quantum numbers. N is 1. It's in the first shell. Now, when n is 1, remember, when n is 1, the only possible value of L is what? 0. So its subsidiary quantum number will be 0. Because there's only one subshell in the first shell. Now, when L is 0, the values of M, which are the what? Which are the magnetic quantum numbers, the values are derived from the value of L. When L is 0, M is also 0. When L is 0, M is also 0. So the possible values of M when L is 0 is only 0. So M is also what? 0. But S is what? S is going to be minus half because the electron is spinning the electron is spinning anti-clockwise. Now let me take a last one for you. Let's write the quantum number for this electron. Let's write the quantum number for this electron here. Let me try and shade that in red. Let's write the 4 quantum numbers for that electron. I'll draw it out in pink first, then write its quantum numbers. I want to keep it close so that I can use the diagram. So, pay attention, please. So, first thing I need to check is, what's its principal quantum number? Its principal quantum number is 2 because it is in the second shell. When n is 2, L is 0 or 1. These are the possible values of L when n is 2. But 0 for 2s, 1 for 2p. Now check, where is this electron located? Is it in the 2s subshell or in the 2p subshell? The electron is in the 2p subshell, so its L value will be 1. Do you understand what I'm saying? So its subsidiary quantum number is what? 1. Magnetic quantum number. Remember, we said when L is 1, we also said when L is 1, the possible values of M are -1, 0, or 1. -1 for, for the X orbital, 0 for P and 1 for Z. Sorry, Y, Z, X, Y, Z. So 2px, 2py, 2pz. But check your electron. Where is your electron located? My electron is located in the middle. So it's located in the 2px orbital. 2py orbital, I mean. Okay, let me try and write this here. This is for 2px, 2py, 2pz. So 0 for this. No, -1 for this, 0 for this, 1 for this. So take note of that. That means the value of M for my electron, because it's in the center, it's in the middle orbital, is what? The value of M is going to be 0. Then go to the last one, the value of S. Check your electron. Is it spinning upwards? +½ If it was spinning downwards, it will be -½ So these are the 4 quantum numbers of this electron. So that's how we write the quantum numbers of an electron in an atom. Feel free to play with any electron in an atom after writing out its what's it called correctly. After writing out its quantum electron configuration like this correctly, you can submit any of your attempts in the comment section so I help you check it. Good luck.